morning all. Today we are going to discuss about the introduction to natural language processing. Today we are diving into the fascinating world of natural language processing or NLP. NLP is a field of artificial intelligence that allows computers to interact with human language, whether it's understanding text, speech recognition, or generating language. NLP is revolutionizing how machines understand and process human communication. Let's break down the key concepts. The first one is text pre-processing. Before NLP models can analyze or generate language, the text needs to be prepared. This is called text pre-processing. The first step is tokenization, where the text is split into smaller unit words, phrases, or sentences. Then we lowercase the text to ensure consistency. This means that apple and apple are treated the same. We also remove punctuation and stop words, those common words like the or is that don't add much meaning. Next, we apply stemming or lemmatization. This reduces words to their base form. For example, running becomes run. Finally, part of speech tagging helps identify the grammatical roles of words like nouns, verbs, and adjectives. The second one is text representation. Now, for computers to understand text, it has to be represented numerically. There are several ways to do this. First, we have the bag of words model, which represents text as a collection of words, ignoring their order. TF-IDF improves on this by weighing the importance of words based on how frequently they appear in a document compared to the whole dataset. Next, we have word embeddings, which represents words as vectors. Models like word-to-vec, globe, and fast text capture relationship between words. Finally, contextual embeddings like BERT and GPT consider the surrounding words, providing deeper understanding. The third one is the NLP tasks. NLP involves a variety of tasks. Let's explore some of the key ones. Text classification. Categorizing text into predefined labels such as spam detection or sentiment analysis. Named entity recognition. Identifying specific entities in the text like people, locations, or dates. Sentiment analysis. Determining whether the text expresses positive, negative, or neutral sentiment. Machine translation. Automatic translation text from one language to another. This task has seen huge improvements thanks to neural machine translation. Speech recognition, converting spoken language into text. Text generation, creating human-like text based on a given input. Models like GPT-3 excel at this task. Question answering, answering specific questions based on a given text or document. Deep learning in NLP. So deep learning has transformed NLP. Models like recurrent neural networks and long short-term memory networks are used for processing sequential data. However, transformers are the real game changer. These models like BERT and GPT can process data more efficiently and capture long-range dependencies in text. Next is the applications of NLP. NLP has practical applications in many fields. Here are some examples. Chatbot and virtual assistants like Siri or Alexa use NLP to understand and respond to queries. Content recommendation. NLP analyzes user content to suggest relevant articles or products. Search engines like Google use NLP to interpret queries and return relevant results. Healthcare. NLP helps extract information from medical records or research papers. Legal and compliances, automating document review and contract analysis. Social media monitoring, analyzing posts for sentiment or detecting fake news. The next one is the challenges in NLP. Despite its advancements, NLP still faces challenges. For example, ambiguity words can have multiple meanings depending on context. Sarcasm and irony are still tricky for machines to understand. There are also issues with low-resource languages where data and tools are scarce, and models can be biased if trained on biased data, which raises concern about fairness and ethics. The next is the tools and libraries for NLP. There are several powerful tools and libraries available for NLP. The first one is NLTK, a popular library for linguistic analysis. SPACY, known for its efficiency and wide range of NLP tasks. Transformers, a library by Hugging Face, which provides state-of-the-art models like BERT and GPT. GenSim, focused on topic modeling and document similarity. TextBlob, great for simple tasks like sentiment analysis. In conclusion, NLP is an exciting and rapidly evolving field that making it easier for computers to understand and interact with human language. With the rise of deep learning, NLP models are becoming more accurate, but there are still challenges to overcome, like bias and language diversity. NLP tasks in syntax, semantics, and pragmatics. Now we are going to explore the key tasks in natural language processing or NLP divided into three essential areas: syntax, semantics, and pragmatics. These areas help computers understand and process human language more efficiently. Let's break down each of them and look at the tasks involved. Syntax task in NLP. First, let's talk about syntax. Syntax deal with the structure of sentences, how words and phrases are arranged to form meaningful sentences. Here are the key tasks in syntax. The first one is the part of speech tagging. The goal here is to identify the grammatical category of each word in a sentence. For example, in the sentence, the cat sleeps, we tag the as the determiner, cat as the noun, and sleeps as a verb. Syntax parsing. This involves analyzing the grammatical structure of a sentence by creating a parse tree or dependency tree. For example, the cat sleeps on the mat shows us how different parts of the sentences relate to each other. Constituency parsing. This task breaks a sentence into subgroups called constituents, like noun phrases or verb phrases. For instance, in the cat sleeps on the mat, the cat is a noun phrase and sleeps on the mat is a verb phrase. Dependency parsing. Here, we identify the relationship between words, showing how one word depends on another. In the cat sleeps, cat depends on sleeps, while sleeps is the root of the sentence. The next one is semantic task in NLP. Next, let's dive into the semantics, which focuses on the meaning of words, phrases, and sentences. Here are the core tasks in semantics. The first one is named entity recognition. This task identifies and classifies proper names like people, places, or organizations. For example, in Apple Inc. was founded by Steve Jobs. NER recognizes Apple Inc. as an organization and Steve Jobs as a person. Word sense disambiguation. Many words have multiple meanings. WSD helps determine the correct meaning based on the context. For example, in the sentence, I went to the bank to fish. Word sense disambiguation would recognize whether bank refers to a financial institution or the river side of a river. The next is the semantic role labeling. SRL identifies the roles that words play in a sentence, like the agent or recipient. For example, in John gave Mary a book, John is the agent, the giver, Mary is the recipient, and book is the theme, the thing given. Sentiment analysis. This task determines the sentiment behind a piece of text, like whether it's positive, negative, or neutral. For example, I love this product is classified as positive sentiment, while I hate waiting is negative. Conference resolution. This involves identifying which words or phrases refer to the same entity. For example, in John went to the store, he bought some milk. Co-reference resolution would link he to John. Pragmatic task in NLP. So finally, let's look at pragmatics, which deals with how context influences the interpretation of meaning. Here are the key tasks in pragmatics. The first one is dialogue systems, conversational agents. These systems understand and generate natural conversations. Virtual assistants like Siri or Alexa use pragmatics to interpret user requests based on context and respond appropriately. Speech act recognition. This task identifies the intention behind a statement. For example, could you pass me the salt? Is recognized as a request, not just a question. Implication and inference. Sometimes meaning is implied rather than directly stated. For example, it's getting late might imply that the speaker wants to leave. This inference comes from context, not the literal words. Disclosure analysis. This task focuses on how different parts of a conversation or text are connected. For instance, now that you mentioned it, I remember. Links back to a previous point in the conversation. Pragmatic ambiguity. Sometimes language can be ambiguous based on context. A sentence like, yeah, right, could be sarcastic or literal, depending on how it's said or the situation. In conclusion, NLP tasks can be grouped into three key areas: syntax, semantics, and pragmatics. Syntax deals with sentence structure, semantics with meaning, and pragmatics with context and real-world usage. These tasks are essential for NLP systems to understand and generate language in a way that is meaningful and contextually appropriate. The next one is the role of machine learning in probability, basics, and information theory. Now we explore how machine learning relates to probability basics and information theory. These two concepts form the backbone of many machine learning algorithms, enabling them to make predictions, classify data, and even generate new informations. Let's dive in. Machine learning and probability basics. First, let's talk about probability basics. In the context of machine learning, probability is used to model uncertainty and make informed decisions. What is probability? Probability helps us quantify uncertainty. It's the likelihood of an event occurring, ranging from 0 impossible to 1 certain. In machine learning, we use probability to predict outcomes and assess how likely different scenarios are. Conditional probability. One of the key concepts in probability used in machine learning is conditional probability. This is the probability of an event happening given that another event has occurred. For example, if we want to predict whether someone will buy a product, we might condition on the fact that the person has visited the website. We calculate the likelihood of this purchase based on the information that the person has shown interest. Bayes theorem. Bayes theorem is another fundamental concept in probability and machine learning. It provides a way to update the probability of a hypothesis based on new evidence. In simple terms, it's about adjusting our belief with new information. The next one is the role of probability in machine learning. Machine learning models like naive-Bayes, hidden Markov models, and Gaussian mixture models use probability to predict outcomes. In supervised learning, we predict labels for unseen data, and the model often outputs the probability of a certain label, helping us quantify the confidence in the prediction. Shape. Information theory and its role in machine learning. Now, let's move on to the information theory, which is the study of how we quantify, store, and communicate information. It plays a significant role in machine learning, especially in areas like data compression, model evaluation, and feature selection. What is information theory? Information theory was developed by Claude Shannon in 1940s. It focuses on the fundamental limits of information transmission and processing. One of its key measures is entropy, which quantifies the uncertainty or randomness of a system. Entropy. In machine learning, entropy is used to measure the unpredictability of information contents. For example, in decision tree algorithms like ID3 or CART, we use entropy to decide how to split data into subsets. A feature that leads to higher information gain, that is lower entropy, is preferred as a split point. Information gain. Information gain is a metric used to measure the reduction in entropy after splitting the data based on a feature. It's widely used in decision trees to select the most informative features for making splits. Kullback-Leibler divergence, in short we call KL divergence. Another important concept in information theory is KL divergence, which measures how one probability distribution diverges from a second. Expected probability distribution. It's used in machine learning for tasks like variational inference and in training models like variational autoencoders. Cross entropy. Cross entropy is another measure that comes from information theory and is commonly used in machine learning, especially for classification tasks. It quantifies the difference between two probability distributions, typically the predicted probability distribution and the true distribution. Lower cross entropy means better performance. The connection between probability, information theory, and machine learning. So, how are all these concepts connected? Probability is the foundation for decision making in machine learning, helping us model uncertainty and predict future events based on data. Information theory provides the tools to measure uncertainty, understand the quality of information, and optimize algorithms for more effective learning. Machine learning algorithms combine these two to build models that can predict, classify, and make decisions with a solid understanding of uncertainty and the quality of the information they are processing. Next one is the role of machine learning in language modeling and estimation. Collocations in language models. Next, let's explore collocations. In language, collocations refers to pair of group of words that frequently appear together more often than would be expected by chance. For example, fast food or strong coffee are common collocations. Importance of collocations. In machine learning, recognizing collocations allows us to capture more natural language patterns. By accounting for these word combinations, models can produce more fluent and accurate predictions. Collocations are particularly important for tasks like machine translation and speech recognition. Next is the N-gram language models. Now, let's move on to the N-gram language models, a popular approach in probabilistic language modeling. What are N-grams? An N-gram is a sequence of N words in a row. For example, a 1 gram that is called unigram might be just the word dog. A 2 gram, which is bigram, could be the dog. A 3 gram, it's trigram, might be the black dog. N-gram models work by calculating the probability of a word occurring based on the previous N1 words. These models are foundational in many NLP tasks, such as speech recognition, text generation, and machine translation. N-gram probabilities. The probability of an N-gram is calculated as the conditional probability of a word given its preceding N1 words. N-gram models use these probabilities to predict the next word in a sequence. The next is estimating parameters in N-gram models. Now let's talk about estimating parameters in N-gram models. The key challenges here is to estimate the probabilities of N-gram from the training data. Maximum likelihood estimation. It is a common method for a parameter estimation is maximum likelihood estimation. MLE calculates the probability of a word sequence by simply counting the frequency of the N-grams in the training data and dividing by the total number of possible N-grams. While MLE works well with large data sets, it can struggle with unseen engrams, those that don't appear in the training data. Next is smoothing in engram models. This brings us to a smoothing, a technique used to handle zero probabilities for unseen engrams. Why do we need smoothing? In engram models, if a particular engram doesn't appear in the training data, its probability will be zero, which can cause issues, especially in language generation tasks. Smoothing helps by assigning small non-zero probabilities to unseen engrams. Types of smoothing. There are several smoothing techniques. Additive smoothing or Laplace smoothing adds a small constant to each count, ensuring that no engram has a zero probability. Good turning smoothing adjusts the counts based on how often engram occurs to estimate probabilities for unseen engrams. The next one is evaluating the language models. Finally, let's talk about the evaluation. Perplexity. One common way to evaluate a language model is by measuring its perplexity. Perplexity is the inverse probability of the test set normalized by the number of words. A lower perplexity indicates that the model is more accurate and better at predicting the next word. Cross-validation. It is another important evaluation technique. It involves splitting the data into multiple subsets, training the model on one subset, and testing it on the other to ensure that it generalizes well to unseen data. BLEU score. In tasks like machine translation, the BLEU score is often used. It evaluates how close the machine-generated text is to human-generated text based on overlapping engrams. Now we come to the conclusion. So in conclusion, machine learning utilizes probability, information theory, and engram models to model and predict language patterns. Collocations help us to understand word combinations, while smoothing and parameter estimation techniques improve the accuracy of engram models. Finally, evaluating language models with metrics like perplexity and BLEU ensures that our model performs well and produces meaningful results. So with this, we are coming to the end of the first unit of natural language processing. Thank you for listening.